Alright, in this video, we're going to learn how to fill electrons into all of the shells, subshells, and orbitals, so we can configure a so-called ground state electron configuration. First of all, we're going to draw out all of the energy shells and the subshells the way we have drawn out before. So each row represents one principal energy shell or principal energy level, and each row has been split into 1 or 2 or 3 or 4 subshells being labeled with different alphabet letters, okay, S, P, D, F. And I hope you still recall that all of the S has a spheroid shape, all of the P's are dumbbell shaped, and all of the D and F has more complicated shapes. And also I want you to keep in mind how many orbitals. So S subshells always has 1 orbital, and P subshells always has 3 orbitals, and D subshells always have 5 orbitals, and 7 orbitals on the F subshells. Now each orbital holds up to 2 electrons. Now all of those things are the basic principles how to put electrons into these subshells. And here we're gonna see what's the order of putting electrons. Okay, so here's how it's gonna look like. The first electron goes into 1s, as well as the second electron. Okay, because electron goes from lower energy subshells to higher energy subshells. Okay, so when the number goes up, energy goes up. So the electron will start from the lowest principal energy level. Okay. Now next one is going to be 2s. Excuse me. And after 2s it's going to be 2p. After 2p it's going to be 3s. After 3s it's going to be 3p, and followed by 4s. And the line goes diagonally like that. Then this indicates the short order of electron will be filled into each subshell. So you can see the electron goes in 1s and 2s and then 2p and then 3s and then 3p and then 4s and then 3d, 4p, 5s, and it goes on like that. Okay, this will be the only way that electrons will be filled into different subshells. Okay. Let's write it out. Okay. If I want to remind you a few basic numbers. So remember we made up a table look like. Just to recap a few quick facts. Okay. So S, P, D, F. It has 1 orbital, and 3 orbitals, 5 and 7 orbitals. A number of electrons will be 2, 6, 10, 14, because each orbital holds up to 2 electrons. Okay, so basically double the number of orbitals becomes the number of electrons. Now, according to the order we have learned here, okay, let me write it out. Configuration. Long or complete electron configuration. Okay. If we have electrons completely filled up all of the orbitals, the electron configuration should look like this. Now, 1s represents the first subshell. Okay, first main shell, first subshell, and the use of a little number on top indicates how many electrons in it. So let's say we filled up 1s with 2 electrons. It cannot go above 2, okay? So it's going to be 1s2. The 2 is indicates the number of electrons on the right up corner here, followed by after 1s is 2s, and then it's 2p. So almost given no space, okay, you can write out 2s Again, 1s and 2s, they have the same shape, same capacity of electrons, 2 electrons, and followed by 2p. P orbitals, 2p subshells has 3p orbitals. Okay, so it holds up to 6 electrons. So it indicates 6 electrons. And after 2p, you have 3s and then 3p. Let's keep going. 3s, 2, and 3p, 6. After 3p, it's actually going to be after 3s, after 3p, it's going to be 4s. So 4s, again, just like 3s and 2s and 1s, okay, it's going to hold up to 2 electrons. And after 3p, 4s, next one is going to be 3d. 3d is going to have 5 orbitals with 2 electrons in each, so it would hold up to 10 electrons. So it goes up to 10. And this goes on, okay, if you want to. And this goes on to, after 3d, it goes to 4p, 5s, 4p, 6, 5s, 2. And if you want, this goes on and on. It goes after 4p, 5s, it goes back to 4d. So it goes to 4d. It doesn't matter if it's 3d or 4d, okay, they all have the same capacity, 4d10. And then this goes on. Okay, so this is a complete electron configuration, meaning every atom, so okay, it doesn't matter how many electrons you have, you're gonna follow this sequence, follow this pattern. Okay, it's just a matter of every atom has different number of electrons. Okay, so let's take a look at a few simple atoms. Okay, so lithium, barium, boron, and carbon. Okay, so let me draw it out here. Okay, let's say lithium. It has 3 electrons. Okay, beryllium has 4 electrons. Boron has 5 electrons. Carbon has 6 electrons. Let's take a look at each one of these, what the electron configuration will look like. Okay, so electron configuration will look like when you have lithium, 3 electrons, it starts from 1s, so 1s2. So you try to add up little numbers up to 3. So there are 2 electrons in 1s, and then 2s. You have to follow this sequence. Okay, 1. So you can see it adds up to 3 electrons. Beryllium has 4 electrons. It's going to be 1s2. Now you have 4 electrons. You have 2 here already, so another 2 electrons on 2s. So that makes up 4 electrons. And boron has 5 electrons. You can see it's going to be 1s2, 2s2, but that's only 4. Okay, so it has 5 electrons. The 5th goes on to 2p. Now instead of 6, okay, it only has 1 more electrons left over. So it's going to be 1s2, 2s2, 2p1. The carbon has 6 electrons. So it's going to be 1s2, 2s2, 2p2. So now we know not only just the number of electrons each guy has, but also how they are distributed around the nucleus. Okay, so you can see lithium has 3 electrons. We used to be able to do this 2, 1. So that's first shell. So that's second shell. Now we know that on the first shell it's located on the s subshell. On the second shell, 1 electron located on the s subshell as well. Similarly, this is 2, 2, and this is 2, 3. So you can see you have 1 electron on the first shell, 3 electrons on the second shell. Okay, 3 electrons on the second shell, but these 3 electrons are not exactly the same. There are 2 electrons on 2s2, 1 electron on 2p1. And the carbon as well, you have 2, 4. So you can have 1s2 electrons and 2s2, 2p2, 4 electrons on the second shell. Okay, so this is electron configuration. Now let's take a look at more. Okay, we not only know that S and P and all those things, so we'll also know that we're going to draw out the electron diagram. Okay, so-called orbital diagram. So let's draw the orbital diagram. This is the electron configuration. Okay, let's draw the orbital diagram. For lithium, okay, we're gonna use one box representing one orbital. Remember what one orbital is? Let's recapture, okay. Now this is one orbital, this is another orbital. So you can see there's only one orbital on S, another one orbital on S. This is 1s, this is 2s. And there are 3 more orbitals on P, okay. So P sublevel has 3 orbitals, and that's why it has a capacity of 6 electrons, 2, 2, 2. Okay, so each orbital holds up to 2 electrons. And also you want remember that the difference between 1s and 2s is 2s has higher energy than 1s. Okay, and then 2p, all these 3 2p orbitals has higher energy than 2s. But these 3 2p orbitals, there are no difference, okay, in terms of energy or shape. They're the same. They're just pointing at different orientations. So when you draw the orbital diagram, okay, 1s is one orbital, okay, and then 2s is another orbital. 2s is another orbital, okay. So and you want to separate these 2 boxes to representing these are 2 orbitals, and there's an energy difference. And the electron is only supposed to fill up the lower energy orbital before you jump to the higher energy orbital. So whenever you have electrons coming, okay, you're gonna use a single arrow representing 1 electron. So lithium has 3 electrons. So the first electron goes here. And because of the shell vacancy, okay, so second electron goes here as well. Now the 1s orbital is completely filled. The third electron will go on to the next orbital, which is 2s. Okay. Now here we need to expand something though. When you say we're using the single arrow representing electron, okay, every one single arrow is 1 electron. Why there are 2 electrons pointing at opposite directions? This is called the Pauli exclusion principle. You don't have to know why is that, but you just make sure you know there's something like that. Okay, Pauli exclusion principle says that an atomic orbital can hold up to 2 electrons, and these 2 electrons must have opposite spins. Okay. So what does that mean? What does electron spin means? Okay, this is just a quick explanation. Okay, so electron is a tiny particle with a negative charge. Now this is one of the features of any micro subject. Okay, it rotates, it spins basically. Now when a negative charge spins at certain directions, okay, it's basically generating a very small, very localized magnetic field. So basically when you rotate at one direction, you're equally saying this is generating a magnetic bar. Now, when you have the second electron, well, which is located at in the same orbital with the first electron, naturally it would tend to have opposite direction if you treat both electrons as magnetic bar, which means the other electron here is going to spin at the opposite direction. Obviously, it's not hard to understand. Okay, if you have 2 magnetic bars spin at the same direction or laid out at the same direction, they're not going to hang out together anymore. Okay, they're going to repel each other. In order to be able to locate a spot in the same orbital, they have to have opposite spin directions. So that's basically the reason. So let's re-summarize everything we've learned so far. Okay, first of all, we have to know how many electrons can be located into can be put into each or sublevels, okay, depending on different type of sublevels, S, P, D, F. And second of all, you have to follow the sequence. This is the energy sequence. Okay, you have to fill up the lower energy orbital before you go to, or sublevel before you go to higher energy sublevels. And in each orbital, okay, in each orbital you can have 2 electrons, one electron spin up, one electron spin down. Okay, point up, point down. Okay, you can have half empty or half filled orbital like this one. You can have only one electron and leave the rest of the orbitals empty. That's fine, but you can only put no more than 2 electrons in one box or one orbital. Each box represents one orbital. Okay, and they have to spin at opposite directions. Okay, there's one more thing we need to learn next. Okay, we'll see. So beryllium has 4 electrons. So similarly, you're gonna have 1s and 2s, and 1s has 1 electron, 2 electron, 2s has 1, 2. So in total, you have 4 electrons. Okay, and then boron. 1s, 2s. Boron has a 1s2, 2s2, 2p1, 5 electrons. Now let's see. 1s1, 1s2, 2s1, 2s2. That's 4 electrons. Now when you draw 2p sublevel, okay, 2p sublevel is a little bit different from 2s and 1s. 2p sublevel, there are 3 orbitals. Remember that picture I showed you? Alright, 1s and 2s can be represented by 1 box each. But 2p, there are 3 boxes. Not only that, these 3 boxes are basically identical. Same shape, same size, same energy. They're just pointed in different directions. So when you draw 2p orbitals, and same with d or f orbitals, okay, you have to draw out correct number of orbitals. There are 3 of them. Okay, 1, 2, 3. And I leave no gap between these 3 orbitals, showing that these 3 orbitals, they are equal in terms of energy and shape and the size, everything. Okay, so there's no preference when you have 1 electron to come in here. Okay, there's no preference. The 1 electron could pick any one of these 3. It's like you're entering a 3-bedroom house. You can pick any one. Okay, there's no preference. So the electron basically come in as 1 electron. So that's 5 electrons for boron. Now the carbon has 1 more electron than boron. Okay, so we're gonna skip the early part. Six electrons. 1, 2, 3, 4. Here comes the last rule about filling electrons. Okay. When you have 5 electrons and 6 electrons come in after the last electron comes in, okay, when you have empty room like this, and there's no energy difference, okay, there's no energy difference, the electron tend to have its own orbital instead of being paired with another occupied room already. Okay, so you will never see anything like this when you have a pair of electrons while other empty rooms are available to you. Okay, especially when there's no energy difference. Okay, if it has higher energy, then yes, you have to occupy the lower energy orbital first. But these 3 has no energy difference. Not only that, if you occupy another empty room, okay, you have to follow the same spinning direction as the first electron. So the reason is simple. If you have 1 electron in one room, another electron in another room or another orbital, and with opposite spinning direction, they're going to be attractive to each other. So eventually they're going to move close into enough to be in the same orbital, and that's never going to happen. Okay, so in order to stay in 2 separate orbitals, they're going to have to maintain the same spinning up directions. They can be both up or both down, okay, but that's okay. They just can be 1 up and 1 down in 2 separate orbitals. Okay, so that's carbon. I'm hoping this few examples will already give us pretty good idea about how to use electron configuration and the drawings to show the electron configuration and the orbital diagram. So these are 2 things we're trying to do here. Okay, you can pause here, see if you can try to do a couple more. Nitrogen, oxygen. Okay, you can pause here, see if you can draw out the electron configuration and orbital diagram. Okay, when you come back, let's take a look at the nitrogen, okay, which has 7 electrons, oxygen has 8 electrons. Alright, nitrogen has 7 electrons. Let's draw the electron configuration. Follow the same trend, okay. 1s2, Focus on the little numbers on top, make up to 7. 2s2, that's 4, 2p3. So we're trying to make 7 electrons. Okay, now let's look at the orbital diagram. 1s2 is a box, 2s2 is one box, and 2p3 are 3 jointed boxes. Okay, the electrons are going to be 1s2 fully occupied, 2s2 are also fully occupied. Now 2p3 can hold up to 6 electrons. Obviously this is only half occupied, so do one at a time. Okay, 2p1, 2p2, and 2p3. Remember, the electrons tend to occupy the empty orbitals when there's no energy difference, like in the case of 3 2p orbitals. Okay, so they will not pair up to each other unless there's no empty room. But this 2p orbitals can still hold up to 3 more electrons. Okay, so let's take a look at the oxygen. Oxygen has 1 more electron than nitrogen, so everything is pretty much the same. 1s2, 2s2, 2p4. Keep in mind that p holds up to 6 electrons. Okay, now the diagram, the orbital diagram: 1s, 2s, 2p. One s1, 1s2, 2s1, 2s2. Oxygen has 8 electrons, that's 4. 2p4, 2p1, 2, 3. Now, all 3 orbitals are occupied equally, so when the 2p4 electron comes in, it has to occupy paired with one of these 3 single electrons. Doesn't matter which one, with opposite spinning. Okay, so this is 2p4. So you can see it still has 2 vacancy here. Okay, before you jump to next orbital after 2p, which is 3s. Okay, so this is, now you can see by doing this we have much more detailed information about where electrons are located and how they're moving around the nucleus. Okay, so we usually say when you have 2 electrons located in the same orbital, like these two, okay, we call them paired electrons. Okay, and then when you have this kind of electrons, we usually call them single electrons. Since they're not paired, okay, they're single electrons. So one of the key information about once you draw the electron configuration and the orbital diagram is you can tell not only how many electrons, but also how many pairs of electrons, how many single electrons. Okay. The other thing is when we talk about electron around the nucleus, so one of the key information we have to get out is valence electrons. Valence electrons, for instance, in the case of nitrogen, oxygen, okay, by definition, valence electrons are supposed to be the electrons located on the highest main level or principal level. For example, oxygen. Oxygen has 2 levels, 1 and 2. Okay, has two levels. Well, level 2 has been split into 2 sublevels, 2s and 2p4, but they both still belong to a second main level. By definition, okay, the valence electrons are all the electrons on the second level, 2s2, 2p4, which is 6. We've learned how to count the valence electrons for main group elements from the periodic table. Okay, so in this case, we can see we now not only know how many valence electrons, we can even write out the valence electron configuration. For instance, oxygen has valence electron configuration of 2s2, 2p4. If you highlight the atomic diagram, okay, it will be these 6 electrons. So you can see 2s2 and 2p4 has 2 pairs and 2 singles. So that's basically saying there are 6 valence electrons for oxygen, and 4 of them are paired, 2 of them are not paired or singles. Okay. Similarly, you can see the case of nitrogen. The valence electrons are 2s2, 2p3, and you can see there's only, even though there are 5 electrons, but there's only 1 pair and 3 singles. Okay. Carbon has valence electron configuration of 2s2, 2p2, and there are 1 pair and 2 singles. Boron has valence electron configuration of 2s2, 2p1, 3 electrons, 1 pair, 1 single. And barium has 2 valence electrons, and these are all valence electrons configurations. There's only 1 pair for barium. Alright, so we've learned that how to draw the electron configuration, orbital diagram, and how do we identify the valence electron configurations.